All right. Good morning, good evening, good afternoon, good middle of the night, whenever you're watching this. I'm going to do a lecture to follow up on levers and functions of simple machines in the human body. I again want to preface that it is extremely, I say difficult. It's not difficult to say it, but we have to remember that your body will apply leverage based on the demand or what you need. So in other words, it's not as accurate to say the knee is a certain type of lever, the ankle is the hip is a. It depends on how you're using it. And what I mean by that is you may say, well, wait, the ankle is an ankle joint. That's that's consistent. How can it change? And I say, well, the ankle's axis is consistent, but depending on the muscles, sometimes you only need a group of muscles. And based on if that lever, that segment's off the ground, it can have a certain function. But sometimes you need both groups of muscles. What I mean by that is imagine if you are balancing on one leg or one foot. So this foot's off the ground and you're balancing on your right leg. You know that when you're balancing, you sway. It may not be crazy sway, but you're constantly shifting your center of pressure over your base of support. And what I mean by that is your base of support is the surface area that your foot creates. And you're constantly swaying. Now, what's responsible for changing that pressure as you sway? Different muscles on each side. Your inverters and your everters are both working at your subtalar joint to balance you, almost like someone who's doing a balance beam and they have that long bar across. You constantly see them wobble it back and forth. That's them swaying. It's an illustration of what's happening down at your foot. But my point is that if you need balance, you are going to need first class type function of balancing multiple forces. Now, your weight is really what you're balancing, because the weight of your body hopefully is going to be on the axis itself. And what your muscles do is basically just like a level. If you have a level and you see a little bubble, and if you rock it this way, the bubble goes that way. And if you rock it this way, the bubble goes that way. It's the same thing. Your center of gravity, your center of mass is the bubble. And if your center of mass starts to shift too laterally to take you this way, well, then your muscles are going to pull and bring the bubble over here. It's kind of like a reverse bubble. And so your muscle groups, your inverters, your everters, even your dorsiflexors and plantar flexors are constantly kind of working in this two-dimensional wobble to help balance you, to keep your center of mass, your center of gravity, as much over the axes as you can for balance. So that's just an example of how we can't say like the subtalar is or the ankle is. It depends on what kind of function you need. And if your feet are off the ground and I need certain muscles to plantar flex, right? So let's say I'm plantar flexing. Well, then if these are the muscles responsible for this specific joint motion, then we can look at, well, this muscle's applying a force here. This is the axis. This is the resistance way over here. Look at the advantage the resistance has way over here. So therefore, the muscle, we need to be specific with our muscle. So let's say I'm talking about the triceps surae, the gastrocnemius and the soleus. Look how close this muscle is applying its force to the axis. Therefore, this force must be a lot greater in magnitude than this resistance. And the trade-off is because this force is very close to the axis, if I can get my muscle moment to be greater than my resistance moment, then the trade-off is going to be speed and range of motion at the distal segment. So you think about jumping up in the air, right? You're trying to plantar flex as fast as possible. And one of the mechanisms that we have to do it is our muscles are pulling a lot closer to the axis than our resistance, our toes. Now the trade-off is that these muscles do not have the mechanical advantage of force. So therefore, we have to make up for it by creating more force. Like, even though it may not have the mechanical advantage of force, we can compensate by having the physiological advantage of force. Big calf muscles, huge, big, thick Achilles tendon, right? That's how we compensate for having less mechanical advantage of torque by having more physiological advantage of force. Okay? In addition, we have to look at levers. Muscle by muscle is another way to look at leverage and levers. Let me give you an example. If I could reduce this hip, okay? So what I mean by that is, let's take a look at the knee, and we're going to talk about a couple different muscles here. So again, the knee is well, a lot of the times, I'm not going to say every time, but especially in open chain, when the foot is off of the ground, we can specifically look at the knee as a third-class muscle for the most part. However, some muscles that function at the knee have advantages of speed and range of motion, and some have advantages of torque and moment. Okay, I'll give you an example. Muscles that cross the knee and insert closer to the knee axis, like the biceps femoris and the semimembranosus, semitendinosus, these muscles cross very close to the axis. So for these muscles, short changes in length difference is going to create large sweeping ranges of motion. Like if you step on a rake, short changes in the rake teeth create huge ranges on the knob handle, swinging up and smacking the person in the movie in the face. So the hamstrings, for example, biceps femoris, semimembranosus, semitendinosus, and sartorius, gracilis, all of those muscles that insert relatively close to the axis have great speed and range of motion capability. Now, they have the advantage of speed and range of motion, but they do not have the advantage in torque production. And the reason is because they don't insert very far away. They insert very close to. The good news is that they don't need to have a lot of torque moment. Why? Because usually when you're flexing your knee in open chain, all you have to move is the mass of your leg. That's not a ton of effort. That's not a ton of mass. So that way when you're sprinting and you need to flex your knee really fast, these guys can do that job very efficiently. Now, same joint, same group, knee flexors, but let's look at the gastrocnemius as a knee flexor. Here is a muscle that instead of crossing the knee and inserting very close to the axis, the gastrocnemius starts here, inserts and keeps going and going and going and going and inserts right there on the back of the calcaneus, that little blue dot. So here is a muscle that inserts very far away from the axis. So speed and range of motion is not going to be that muscle's forte. Torque production. And remember, there is a inverse relationship between speed and force. It's a force velocity graph that we talked about. There's an inverse proportion. And guys, one easy way to look at that is if I have a 2-pound dumbbell in my hand, I can flex my elbow a lot faster with a max effort than a 50-pound dumbbell. The more force I add, the slower I have to move with the maximal effort. So the point is, this gastrocnemius inserts very far away. There's trade-offs with that. You know, it's like an athlete that has, you know, maybe a certain ball player has some offensive line, quarterback, wide receiver, some certain routes they run well and some routes they don't run well. Things you can, things you can't. This gastroc inserting very far away in open chain, think about it. It has to contract a huge distance, and that takes time. So if you're trying to flex your knee as fast as you can, you're going to use these muscles that have more third class speed and range of motion advantage versus a muscle that inserts way over here. That would be the slow poke. So what's really cool about that is they have research on this. They have electromyography, and they show that when you flex your knee with significant speed, the gastroc doesn't even turn on. It can't help mechanically. It can't contract fast enough to run around the track all of this way, where these muscles only have to run a short distance around the track. So the gastrocnemius is actually off. Now, when would the gastrocnemius be on in open chain knee flexion? Two things: go slow enough where the gastrocnemius can keep up, or contract strong enough where it has no choice but to be slow. So imagine doing hamstring curls. The gastrocnemius is like, that's my game. That's awesome. You need some extra help for force. You're not going super fast because you need extra help for force. I can help out tremendously. Okay. So again, it's a practical example of why we don't necessarily classify joints as levers. We have to look at the joint and the different muscles that pull, because some muscles pull closer than other muscles. So one of the things we would do at Auburn, we'd talk about classification of muscles, like the gastrocnemius in open chain is more of a second class advantage of muscle pull. And when I say second, I'm just saying that that muscle has the disadvantage of speed and range of motion and the advantage of torque production. So it's almost not even like seconds, thirds, firsts, or I'm trying to actually make it easier for you. It's what is the advantage you need? What do you need? If you're trying to move fast, you're going to need first class arrangements that favor speed, and you're going to need third class arrangements because those always favor speed. If you're trying to move something heavy, you're going to need first class arrangements that favor torque because that's naturally going to be slow, and you're going to need second class arrangements because they always favor torque, and they're usually always slow. And if you need balance, if you need to balance, and that means balancing on your ankles, with your feet on the ground, you could be doing push-ups and you need to balance with your hands on the ground. That's when you're going to typically use first class arrangements where the axis is the joint and the forces are actually muscles on each side of the joint. Like imagine if my arm's on the ground, I'm going to need horizontal adductors, abductors, flexors, extensors, all working on like a weeble wobble board to help keep my weight over my center of mass. Okay, so the easiest way to determine leverage is, what do you need? Okay, in biomechanics we talk about having ankle and hip strategies for balance, and I want to explain why. Because in the ankles and the hips you have weeble wobble options that you don't have at the knee. Remember, guys, the knee can only do this and this. The knee can only flex and extend. Well, what about internal, external rotation? Yeah, that's for a different function, but I'm talking about balancing. Here you have plantar flexion, dorsiflexion, plantar flexors and dorsiflexors, and inverters and everters. So you cover all of your bases. Guys, transverse isn't really a balance option. We're really talking about sagittal and frontal, keeping your butt from falling on the ground. And the ankle and subtalar joint provide that. Ankle supplies the sagittal balance, and the subtalar provides the frontal balance. When you get up into the hip, you get all in one place, right? You get sagittal balance with your hip flexors and extensors, and then you get frontal balance from abductors and adductors. In addition, you can make it harder or easier if you have both feet on the ground. Well, now it's really cool because you have right hip, left hip, and you can look at the center of mass of your pelvis. So it's kind of like you have these muscles kind of influencing this side of the balance beam, and then you have these muscles influencing this side of the balance beam, and your center of mass is actually going in between your feet. Your center of mass is here, and here is your base of support. So it's kind of neat. You have these groups of muscles working on this side and these groups of muscles working on this side to balance your stuff that's in the middle. Balance. If you're sprinting as fast as you can and you need to flex your hip as fast as you can, which by the way is the limiting factor to how fast someone is hip flexion speed. Remember, you got to do a couple things. You got to speed up hip flexion, and then you got to slow down hip flexion. So let's talk about leverage of muscles that might be of an advantage for each of those things. Speeding up hip flexion. I need to flex as fast as I can. Speed, third class or first class with speed function. In other words, I need muscles that insert relatively close to my hip axis. Well, my iliopsoas inserts right there. That's pretty close, right? My iliopsoas, that's kind of a speedy muscle. And so my iliopsoas would be a great speeder upper of hip flexion. Look at it, pulling right there on the lesser trochanter. It only has to contract a short distance to get a huge sweeping hip flexion motion at the distal end. Okay, so the iliopsoas is an example of a third class functioning muscle when you're trying to flex your hip as fast as you can when you're running. Now I taught you what speeds up must slow down. So once you generate the speed of the hip flexion, well, what's going to slow you down? Well, it takes a lot of force to slow down momentum of joint motions, right? Just like putting on the brakes of a car. It takes a lot of force if you're trying to slam on your brakes. In fact, slamming on your brakes will wear away your brakes, and you're going to have to change the brakes. Guys, this is the secret to delayed onset muscle soreness. Where does the damage come from exercise and daily and sport activity? It's from the brakes slowing down motion. So my point is that we have to slow down hip flexion. Well, I have hip extensors that insert very far away, like my hamstrings, semimembranosus, semitendinosus, biceps femoris. They insert very far away, so they have the mechanical advantage of torque production. Putting on the brake, and yes, my gluteus maximus can slow me down as well. It doesn't quite have the torque, but it compensates with huge muscle mass. It compensates for what it lacks mechanically inserting super far away with what it has physiologically, and that's just a big chunk of meaty glute muscles that can really help to slow me down. So pulling hamstrings or sore hamstrings, that's from the slowdown mechanism, okay? So that'd be a second class. Now, I got to speed up the hip extension. Gluteus maximus can help me do that. And remember, speeding up the hip extension doesn't just happen in open. That's when your feet are going to be on the ground, weight bearing. So it's going to take a heck of a lot more strength than normal to do that. So that's again why the gluteus maximus kind of inserting somewhere in the middle. Remember, power lies in the middle. Power is a combination of speed and force. It's Goldilocks and the Three Bears. It has to be just right, not too far away, not too close, somewhere in the middle. Deltoid, somewhere in the middle. Gluteus maximus, somewhere in the middle. So when my feet's weight bearing and I'm trying to continue to extend the hip, I need some power with that. Okay. Now, once my hip extends and my foot leaves the ground, I need to slow down that hip extension. My iliopsoas pulls in a direction of flexion. It can help slow down the extension, but man, mechanically, it does not have good leverage arm for torque, for peak torque. It's a speed muscle, but to slow down that hip extension, I need a hip flexor that inserts far away. Rectus femoris, anyone? So your rectus femoris is a great breaker muscle because of its second class feature. It inserts far away. Now, if you say, well, wait, I thought the rectus was a knee extensor. I'm talking about its function at the hip. It has a second class function at the hip because it inserts so far away from the hip joint. It has a third class function at the knee. Okay. So I'm just trying to show you guys how we can apply these muscle lever concepts to the lower extremity. Does it get more complicated than that? It can. And that's why the Lord invented graduate school, for you to go off and kind of delve into more of these kind of concepts. Weight bearing, obviously, there's a lot of different things that can happen when you're squatting, and ankles, knees, and hips are all working together as a hydraulic lift, and we can look at different muscles pulling on bone, and then the bone pushing, and there's different levers we can look at. But for the most part, what I wanted to simplify in this short lecture today and try to bring everything home is leverage is what you need. If you need balance, you're going to utilize first class leverage. If you need speed, you're going to utilize leverage muscles that supply the speed. If you need torque, you're going to recruit muscles that supply the torque. A couple more practical examples to try to help explain this as well is sometimes in textbooks they'll use these the examples are simple, but the concepts are not. What I mean by that is they may say a push-up is, let's see if I have my chalkboard here. They may say a push-up is an example of a second class lever. And they may have like, there's the feet, and there's the head, and there's the arms. And they may say, you know, here's the axis, and there's the force, and there's your resistance, okay? Now, I'm not saying that's wrong, but that's an oversimplification of what's happening. Muscles are influencing these joints. So in other words, you have levers in the shoulder joints. You have levers in the elbow joints. You have so let me give you another example. Going up on your toes, okay? They'll say going up on your toes is an example of a second class lever. And they'll use the example of, you know, here is the, let's see, there's your calcaneus. So here is the pull of your gastroc, there's your axis, and then there's your resistance. Okay. They'll do something like this. And what I'm trying to get you to see is that there's more here than just that. If we look at a wheelbarrow analogy, right? And there's the hull of the wheelbarrow, and there's your hands pulling up. Here's your axis, and there's your resistance. So in other words, looking at going up on your toes, what we should do is say, no, 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 no. Here's your axis, going up on your toes, your first metacarpal phalangeal joint. That's your true axis. I agree with the resistance, but you know what's happening here at your ankle joint? That would be how the handle of the wheelbarrow rotates about your hands. In other words, if you think about lifting up the wheelbarrow on your hands, the angle change between your hands and the handle in the wheelbarrow analogy, that's actually what's happening here. So going up on your toes is similar to a wheelbarrow, but there's multiple joints. There's what's happening all the way at the wheel, but then there's what's happening between your hands and the handle. I don't mean to say that example to confuse you. That's not my intent. My intent is to tell you there is a lot more to it, and it is not as accurate to say the elbow is a, the wrist is a. It's more accurate to say this muscle that's pulling at the wrist in open chain has an advantage of speed and range of motion because it inserts close to the wrist, and the distal part is free to move. But if I was trying to balance on my knuckles, like if I had my hand on the table and I was trying to balance on my knuckles, well, then now I'd have a first class, because balance, my wrist flexors would be working with my wrist extensors and my radial and ulnar deviators. They would be constantly pulling to balance the weeble wobble. So it's what you need. If you need balance, you're going to recruit certain muscles that allow for first class leverage advantages. The functions of a simple machine: balance multiple forces, that's muscle pull and weight and gravity, usually for the body. Redirect and applied force, I didn't even get to that, but that's where your gastrocnemius pulls back here and the front of the foot goes down because the gastrocnemius is pulling up. Redirection of an applied force. Now, the redirection of applied forces work with the balance. You know, that's the whole point, that when you're balancing, this pulling up here makes the other side go down, this pulling up here. That's the whole thing of the level. I do this, the bubble goes that way, I do that, the bubble goes that way. That's kind of first class redirection of applied forces. So it doesn't have to be one or the other. It could be they serve multiple functions. I'm trying to balance and I'm trying to supply a lot of force. I'm trying to supply a large torque. Second class type muscle arrangements can do that. I'm trying to go as fast as I can. Third class muscle arrangements can do that. Okay. So for the test, because I know you guys are like, Campbell, that's great. What do I need to know for the test? I need you to match up function. If I say speed and range of motion, I need you to automatically think third, or first, that favors third. If I say slow and or massive force, you can't do massive force fast. Think seconds. Okay. There was one more thing I wanted to explain here. Let's see if I can think about it. Oh yeah, I might have said this on a previous lecture, but it bears repeating. Usain Bolt is the fastest man that's ever been on Earth that we know of. I cannot choose to go as fast as Usain Bolt. I can't. Get in a car. I can't choose to run as fast as Usain Bolt. Usain Bolt would be an analogy of a third class muscle arrangement, or a third class functioning muscle at a joint. Close, open chain, fast. Or a first class that favors speed and range of motion. Usain Bolt, fast. Second class arrangements, second class muscles cannot choose to go as fast as thirds. That's the example I gave about the gastroc. If you're trying to flex your knee as fast as you can, the gastroc's, bro, I can't go that fast. However, Usain Bolt can choose to run slow. Usain Bolt can jog. Usain Bolt can walk. So my point is that because maximum effort inherently takes less speed and is slow, that means every single muscle, whether it's third, second, first, can help in that work. If you're doing something slow or forceful, all of the muscles that pull in that direction can help. However, if you're doing something very fast, meaning that it's not max force, because again, I can't flex my elbow super fast with a lot of weight. It has to be light to make it go fast. Then and only then will I only use third class types of muscles. Usain Bolt can choose to run slow, but I cannot choose to run fast. All right, guys. Hope this helped. I'll communicate what's coming next on class email. Check your emails. And check your emails. I have the dates for the final all on there. So Y'all hit me up if you have any questions. Bye.